Sir Isaac Newton was born in England in 1642, 9 years after a pope told Galileo to go to his room for saying the sun didn't revolve around the earth. He spent much of his life doing research in the fields of mathematics, optics, chemistry, and more. But most likely you've heard that he discovered gravity one day as he watched an apple fall from a tree. His real discovery was realizing the same force that brought down the apple also kept the moon in orbit. So, why doesn't the moon fly off into space, and what do we mean by force, and why doesn't the moon fall to Earth? Newton came up with 3 simple rules that explain how objects move, here on Earth and out in space. He included these rules in one of his books published in 1687, called The Mathematical Principles of Natural Philosophy, or simply the Principia. His first law: every object will remain at rest or in uniform motion in a straight line unless compelled to change its state by the action of an external force. His second law: force is equal to mass times acceleration. And his third law: for every action, there is an equal and opposite reaction. And the apple thing? That's his law of gravitation. More on that later. We are first going to talk about motion. The first law says, if an object is not moving, it will not start moving by itself. Something needs to push it. If an object is moving, it will not stop or change direction unless something pushes or pulls it. That something is a force. Forces like friction act between objects that touch. Other forces like magnetism or gravity act between objects separated in space. According to Newton's first law, the moon should continue to move at the same speed in the same direction. So, why doesn't it follow a straight line out into space? It is compelled to change its state by the action of an external force. And the external force? The same force that pulled that apple to the ground, gravity. So why doesn't the moon fall like the apple? It does. Gravity continually pulls on the moon, causing it to fall towards Earth, away from its straight line path. But the moon is moving away from Earth fast enough that the distance it travels away is the same as the distance it falls. So even though it is falling, it moves around Earth at a nearly constant distance. Or, looking at it another way, the moon is always attempting to fly off in a straight line, as Newton's first law predicts. But the force of gravity pulls it into a curved path, like a string keeping a toy rocket in a circular path as you swing it around your head. Newton's second law says that force on an object is equal to the mass of the object multiplied by its acceleration. Written out, it's F equals m times a. Mass is the amount of matter or stuff in an object. We can measure that in grams, kilograms, slugs, and metric tons. Acceleration is the change in velocity over time. If we measure velocity in feet per second, acceleration is feet per second per second. Let's look at a billiard ball. According to Newton's first law, it's going to sit there until a force acts on it. To send it hurtling into another ball at 13.5 miles per hour, we'll need to apply some force to it. How much? We need to find F. Here it is. Let's solve for F. F will be the mass times the change in velocity over time. The billiard ball's mass is about 1/6 of a kilogram. The change in velocity is 0 to 6 meters per second per second. 1/6 times 6 equals 1. 1 what? 1 Newton. named after Sir Isaac, of course. By definition, 1 Newton is the amount of force required to push a 1 kilogram object from rest to 1 meter per second over the course of 1 second, or 1 second squared. And by sheer coincidence, this is the amount of force, or gravity, the Earth exerts on a medium apple. If our moving cue ball rolling across the green fabric of space-time at 6 meters per second clacks into a stopped billiard ball, it exerts a force on the billiard ball, and Newton's third law comes into play. It tells us that the billiard ball exerts an equal and opposite force on the cue ball. The cue ball stops, and the billiard ball moves away at 6 meters per second. Now, let's replace the cue ball with a ball that has twice the mass of the cue ball. If we strike the new ball with the same force, its acceleration will be half that of the cue ball. After the force is applied, the more massive ball will move away with a speed of only 3 meters per second. Newton's laws of motion can show you how fast and in what direction an object will move when you apply a force, whether the force is gravity, the hit from a moving cue ball, or something else. The first law says that an object will keep doing its own thing, moving or not moving, unless something is applied. The second law shows how to calculate or measure that force. And the third law shows us what happens when objects interact. Join us next time for another Your World in a Minute from Starlight Express.